This question is from GATE 2022, Mechanical Engineering paper, question number 51. A cylindrical disc of mass m equal to 1 kg and radius r equal to 0.15 meter was spinning at omega equal to 5 radians per second when it was placed on a flat horizontal surface and released. Refer to figure. Gravity g acts vertically downwards as shown in the figure. The coefficient of friction between the disc and the surface is finite and positive. Disregarding any other dissipation except that due to friction between the disc and the surface, the horizontal velocity of the center of the disc when it starts rolling without slipping will be dash meter per second. Let's find out. So we'll start by writing the given things. Mass of the disc is given 1 kg. Radius is given to be 0.15 meter. Angular velocity omega is given to be 5 radian per second. We need to find out the velocity of center. Let center be C and this point of contact be P. So we need to find out VC, translational velocity of center C. Now it is given that before it starts pure rolling, friction F acts on the disc. But let's assume that when it reaches a certain position over here, it has overcome this friction value F and then it starts pure rolling motion. That means at this point, its angular velocity will be different because the force that was governing the rotation motion, which was friction, has now become 0 and therefore angular velocity of the disc will change. So let the angular velocity at this position, this second position, be omega 2. Now for pure rolling motion, we know that the motion will take place about this point of contact, point P, and therefore linear velocity of the center VC will be written as r into angular velocity of the disc, which is omega 2. So now r is known to us, we need to find out omega 2. From here we can take a hint, angular velocity is unknown, so we can conserve the angular momentum here. Because there is no net torque on the disc, therefore angular momentum will be conserved. We can write down net angular momentum of the disc will be 0 using the law of conservation of angular momentum, as there is no net external torque acting on the disc. So we can write down initial angular momentum as I, mass moment of inertia of the disc, into its angular velocity omega. This is the initial angular momentum. This will be equal to the final angular momentum, which will be I into omega 2. There will also be angular momentum due to translational velocity of center of the disc. So if we assume that the disc is rotating and the center is translating, its final momentum can be written as I omega 2 plus mass of the disc into velocity of the center VC into R. This will give us the angular momentum. M into VC is the linear momentum, into R gives the angular momentum of center of the disc. So in here, you should know the mass moment of inertia of a disc. It's a standard formula. It is given as m into r square by 2 into omega will be equal to again m into r square by 2. Remember, this is not omega, this is omega 2 plus m into VC is written as r into omega 2. So we'll substitute this here, r into omega 2 into r. Simplifying this, we will have, taking mr square common, we can cancel out mr square from both left hand side and right hand side. So we are left with omega by 2 will be equal to omega 2 by 2 plus omega 2, which is 3 by 2 omega 2. We need to find out omega 2. So omega 2 will be equal to omega by 3 and omega is given to be 5 radian per second. So it is 5 by 3. From here we can find VC. VC will be equal to R, that is 0.15 meter into omega 2 is 5 by 3. This gives us VC value as 0.25 meter per second. Let's go back and fill in this answer. So when it starts rolling without slipping, the horizontal velocity of center of disc will be 0.25 meter per second. To learn more about circular motion, you can refer to the NPTEL video lecture 22, circular motion. It's from the course Engineering Mechanics. The course is taught by Professor K. Ramesh. He is from IIT Madras. I hope this helps you clear your doubt. Thank you.